piecewise functions. Our objective for this video lecture: evaluate, graph, and analyze piecewise functions. Okay, so we're going to have to define piecewise functions, but let's start off with reminding ourselves what a function is. All right, so we know that a function is a relation that associates each element of the domain, each input or each x value, with exactly one element of the range, the output or the y value. Since we know what a function is, we can now define a piecewise function. A piecewise function is simply a function that is defined by more than one equation, more than one piece, if you will. Okay, another way to state this: it's a function that behaves differently based on the input value. So the input value is going to determine which equation you use to evaluate the function, because you're going to have more than one equation. I want to bring up another vocabulary term or two that's going to come into play here, and that's the idea of a continuous function. Okay, a continuous function is a function whose graph can be drawn without lifting the pen or the pencil from the paper. So when we talk about functions, usually we're talking about functions being continuous, because usually we can draw them without lifting the pencil from the paper. But when it comes to a piecewise function, this may or may not be the case. So a continuous function, a couple of notes. The graph is a single, unbroken curve. The graph has no gaps or holes. And the opposite of a continuous function is a discontinuous function. And so a function is discontinuous if its graph does have gaps or holes, and so therefore cannot be drawn without lifting the pencil from the paper. So continuous, I can draw it without lifting the pencil. It has no gaps or holes. Discontinuous, I have to move my pencil, I have to lift my pencil to continue drawing the function, or it has a hole in the function. Okay, let's take a look at an example of a piecewise function. So here's one right here. This function f of x, it equals these three pieces depending upon the input value that we're being asked to evaluate. So the function equals x squared if x is less than 2. The function equals 6 if x equals 2. And the function equals 10 minus x if x is greater than 2 but less than or equal to 6. Okay, so back to our definition. Okay, here, a function that is defined by more than one equation. Okay, well, here we have it. Get my paper straightened out for you. Here we have it. This function, it's a piecewise function because it is made up of more than one equation. In fact, in this case, it's made up of 3 equations. It's made up of f of x equals x squared, equation 1, f of x equals 6, equation 2, and f of x equals 10 minus x, equation 3. Just a note, you'll notice that this is a parabola, a parabolic function, x squared. This is the constant function, so it's a horizontal line, and this is a linear function. So it's made up of 3 different functions in this case. So let's do some evaluating, some analyzing, and some drawing. Okay, I'm going to have to move my paper up and down a little bit, but that's okay, we can handle that. First off, let's evaluate this function at these 4 points. Okay, so at x equals 4, at x equals 4. Well, let's see here. We're going to evaluate at x equals 4. What do we know? Well, we have to first, it's different. It depends upon the input value. The input is -4. If I look over here, the function I want to look at is this function because -4 is less than 2. -4 is less than 2. That tells me I want to use this function, f of x equals x squared. Okay, so because -4 is less than 2, this is my function. I'm going to put in -4, which means I'm going to substitute the argument x with -4, and I'm going to square that, and my function's value my function's value at -4 is positive 16. So let's take a look at when x equals 0. Okay, I need to first determine which equation applies. Well, let's see here. Again, it turns out 0 is less than 2. So my function is the f of x equals, the equation is the f of x equals x squared equation. 0 is less than 2. That tells me, okay, I got to use this one. F of x equals x squared. Okay, so I'm going to put 0 into the function, which means I'm going to square 0, and out comes 0. Okay, how about when x is equal to 2? Okay, let's go up here again. Which equation do I choose? Well, 2 is not less than 2, so I'm not going to use this equation, f of x equals x squared. Hey, 2 is equal to 2. So I'm going to use this one, f of x equals 6. So it turns out 2 is equal to 2, which tells me I use f of x is equal to 6. Okay, well, that tells me, okay, put in 2, and out comes 6. And so the value of the function at 2 is 6. Okay, last choice. Let's input the number 6 into the function. Okay, again, first, I need to compare it to see where it fits. Let's see, 6 is not less than 2. 6 is not equal to 2. 6 is greater than 2 and less than or equal to 6. Okay, so I'm going to use this one. So it turns out that 6 is greater than, whoops, I meant to put 6 here. 6 is greater than 2 and less than or equal to 6. So that tells me I'm going to use this function. F of x is equal to 10 minus x. So now I'm going to put 6 into this function. 10 minus, I'll use parentheses just to show you that I'm inputting 6 in for x. I'm substituting, and I come out with the value 4. So when the input is 6, the output is 4. So that's evaluating a piecewise function. You have to focus on which of the 3, the 2, the 3, maybe the 4 equations apply to your particular input. And obviously it's different depending upon the input. Okay, number 2. I'll write down 2 and off the paper, so here I'll slap it down just a touch. What is the domain of our function f? Okay, let's look up here at our function. Domain are the x values that can go in. Well, I can put an x in that's less than 2. I can put 2 in, and I can be greater than 2 all the way up until I get to 6, and 6 is included. So, if I come down to here, my domain in set notation is all x's such that x is less than or equal to 6. Okay, in interval notation, I'm going from negative infinity, so I have the parenthesis up to 6, and 6 is included. It's included here, so I use a bracket. And so there's my domain in set notation and in interval notation. Okay, number 3. I want to talk about the intercepts, and this is where things can get just a little bit complicated with these piecewise functions. The y-intercept, Okay, so I'll put a dot here. Y-intercept is very straightforward. The y-intercept is when x equals 0. Okay, we know that. So, use the equation that accepts 0. Okay, which equation accepts the value of 0? So I go up to here and look at these equations. I have 3 again. Which one accepts the 0? Well, as we saw here, 0 is less than 2. So this is the equation where my y-intercept is going to be. Okay, so this one is, okay, again, whoops, let me see here. So we know that 0 is less than 2. This tells us to use this equation, f of x equals x squared. Let's put 0 in there. And again, we're doing the same thing we just did a couple minutes ago. Okay, so the y-intercept is 0. You can also write this as we put 0 in, out came 0, so it's the point 0, 0 is the y-intercept. Okay, now x-intercept is a little bit different, and I'm at the bottom of my paper, so I'm going to get another piece of paper out. But this will be good because I can show you the top part. If I can keep myself straight here, I can show you the equation, the function itself while I do this. So this is going to be 3 continued, and we're still looking at intercepts. Okay. Well, now we're looking at x-intercepts. Okay, the x-intercept, or intercepts, we know is when y equals 0, or in our case, whoops, f of x equals 0. The function, so we need to have, it's crossing the x-axis. Well, we need to test each piece within its parameters. Okay, so we're going to, that's the x, let me see if yes, sorry about that. Let me get back on my paper. I'm just checking to make sure I'm being consistent. Okay, so we need to solve f of x equals 0 for each piece, for each equation. Okay, then determine where each solution satisfies the condition defining its piece. Where each, sorry, I'm getting lost in my wording here. Where each solution satisfies the condition for its piece. Okay, so let's up just a little bit here. We need to check this piece. Does this piece cross the x-axis? Okay, so our first piece, our first equation is f of x equals x squared, and its condition is x is less than 2. That's our first piece. Okay, let's see. So I want this to be equal to 0. So I want this part to be 0. So to 0 equals x squared. Let's solve that for x. I square root both sides, and I come up with 0 equals, well, plus or minus 0. Whoops, let me go a little bit higher here so you can see that. 0 equals 0. Okay, so that x is 0. Does this satisfy this right here? Okay. Okay, is 0 less than 2? Check. Okay. So it has to satisfy this condition here. So we know that the point 0, 0 is an intercept, or that x equals 0 is an intercept. Now let's look at the second piece. The second piece is f of x equals 6. Now it probably seems pretty obvious. Whoops, let me give it a bit more space, that this is not going to be an intercept because f of x equals 6 is a horizontal line at 6. But we'll go through the process anyways. And this is going to only apply if x is 2. Okay, so let's put 0 in for f of x. Does 0 equal 6? Well, 0 does not equal 6. Doesn't matter about the fact that it doesn't even equal 2. And so there's no solution. So there's no x-intercept here. No from this piece. This piece has no x-intercept. Okay, let's look at our third piece. Our third piece is f of x equals 10 minus x. And the condition to this one is that x is greater than 2 and less than or equal to 6. Does this piece cross the x-axis anywhere? Well, let's put 0 in for f of x and let's solve it. 10 minus x, I'll add x to both sides. I get x equals 10. Well, look, it does cross the x-axis. It crosses at 10. Okay, but wait a minute. Wait a minute. I forgot to put an x here. I messed that up. I got to check my condition. Okay, this is 10 is not between 2 and 6. Okay, so even though this piece, this equation does cross the x-axis at 10, that's outside of my domain. It doesn't fit on in the function. It's outside of the function's domain. So we would say, nope, no solution. Okay, no x-intercept because, let's see here, as 10, no solution. I'll write down no x-intercept. No x-intercept. I'll scroll up a little bit here so you can see it. As 10 is not between 2 and 6. So there you have it. That's how you go through all these. You have to do each piece 0 to 0 equal to 0 equal to 0 equal, and you need to check it against the domain of that piece to see if it's an x-intercept or not. Okay, fourth, let's graph this piecewise function. Okay, so I'm now going to slide this up. And I'm going to kind of have, I'll tell you, I'll move that sheet in. A little bit tougher to work with this, but I'll move that sheet in as I need to. Let's graph it. Okay, so first I'm going to create, I'll create my XY coordinate plane. And I know that I'm going to go, I know I got to have a 2 in here. Let's see here, 1, 2, 3, 4. I'll put a 4 here and a negative 2 and a negative 4. I'll go 1, 2, 3, 4, 5, 6. So this is positive 2, positive 4, positive 6. And 1, 2, 3, 4, 5, 6. That should work. Okay, let's take a look here. I think that should work. Okay, so we know, let's go back to our function. I'll put my function if I slide this over, I can fit my function. I can't fit in very well. Here's my function. Okay, well I'm gonna graph this middle one first. When x equals 2, f of x equals 6. So when x equals 2, f of x equals 6. That's a point right there. Okay? Now, let's go back to this. Before it reaches 2, it's the x squared function. Well, that's one of our library of functions. And so that is all the way to 2. Let's see. It's going to be the x squared function. So let's see. 2 squared is 4. And so here's the x squared function. all the way to 2. Okay, now again, it's not, if I look back at my function, it's x less than 2. That's why I have an open circle. Okay, but this is the x squared function coming in right there. Okay, this continues this way. Now, once I get to 2, f of 2, once x is 2, out comes 6. If I go back to my function, once x is larger than 2, I'm using this. Okay, well 10 minus 2 is 8. And so if I go up here to 8, this line is going to start at 8. Okay, again, 10 minus 2 is 8, but it doesn't, the point 8 is not included. And it's a linear function with a slope of -1. So I'm going to go down like this. Let's see here. And I stop at 6. 10 minus 6 is 4. So here I have the rest of that piece of line. Again, it goes from 2 to 6. 10 minus 2 is 4. 10 minus 2 is 8. 10 minus 6 is 4. So I'm going to go from 8 to 4. And of course, the point 6 is included. So there's my piecewise function. This is the piece. F of x equals 10 minus x. Okay. This is the piece. F of x equals 6. And this is the piece. F of x equals x squared. And that's the graph of this particular piecewise function. Okay? So that you got to graph each piece and then be careful about how do you have holes, do you have dots in this case, single points. This one goes off, this one goes up to positive infinity forever. This one stopped, but this one stops at 6. There's nothing further to the right, etc., etc. Okay, now let's use that graph to answer 2 additional questions. Okay, question number 5. What's the range? Let's use the graph to find the range. Okay, what's the range of this function? Well, the range is a set of y values. So if you want, we could say y such that, well, y's go from 0 to positive infinity. It covers all y's. So all y's greater than or equal to 0. That's the range. Whoops. In set notation. Okay. Any y, there's every value from here above is in the y because of this portion here is going to come out in the range. And of course, in interval notation, this takes you, 0 is included. So 0 to positive infinity, that's the range according to the graph. Letter 6, is this function continuous? Excuse me, number 6, not letter 6. Is this a continuous function? Can I draw this entire function without lifting my pencil? And as I'm sure you're probably thinking immediately, no, you can't. So it's certainly pretty obvious it's not continuous. If I try to draw this, I come in from here, I come down, I'd be good. I get to here, I have to lift my pencil to put this point down. I have to then lift my pencil to start here and go down this way. Plus there are 2 holes in the graph. They're filled by this point, but it's not in the holes. So this function is not continuous. This function cannot be drawn without lifting my pencil from the paper. It has, in this case, it has holes and it has gaps. It's got gaps right here and here. So it's got a variety of things going on that mean it's not continuous. So there you have it. Piecewise functions. Functions, as this example here shows us, that are made up of more than one equation that require you to first determine which equation to use based upon the input.